All right, so homework questions. I'll go briefly through all of these, but if you have specific questions, let's talk about those up front.
So I think it's, what, 3.56? The one is just write out that the square root of 3 is irrational.
Mm-hmm.
I just want to make sure that it just wanted you to write out that statement, right?
Correct.
Okay.
Yeah, it's not a proof question. So let's do that. So state that the square root of 3 is irrational. So did you come up with a way to write that?
Oh, yeah. It was like for all x. For L, there's an x. There's not an x and a y. Yeah. This is like x over that, y. Yeah, that can't be x over y.
Okay.
All y. Yeah.
There exists some x that doesn't equal.
So there does not exist, let me put these in parentheses, an x and a y, such that square root of 3 equals x over y. Right? And I would probably say where x and y are integers, just to be clear. Right, so there's no pair of integers x, y such that square root of 3 equals x over y. Or we could have written such that 3 equals x squared over y squared. Or we could have written such that 3y squared equals x squared. There's a lot of different ways you could write it. We could also write, did anybody come up with a different way to write this?
I'm trying to remember what it was. I'm not looking at it.
Do you have homework?
Yeah.
Okay. So we could also say something like, for all x and y contained in z, square root of 3 is not equal to x over y. We could also write for all x contained in z, there does not exist a y contained in z. Okay. Such that square root 3 equals x over y. So those are all saying the same thing. All right, other questions? So let's see what we had for the homework, 3.1. Question 2, for each of the following propositions, identify simple propositions, express the compound proposition in symbolic form, and determine whether it's true or not. So, I don't know, let's just pick one of these kind of at random. So, 3.1, 2D. So this says 3 is an element of Z and 3 is an element of Q. 3 is an integer and it's also a rational number. And we want to write this as a series of propositions and a compound proposition. So you could do something like, let P be the proposition, 3 is in Z, and let Q be the proposition, that 3 is an element of the rationals. And then this compound proposition is just P and Q. So nothing too heavy going on there. 3.2. So we started looking at some of these proofs. the other day. Any particular questions from 3.2 that? So there was one question which was constructing. I was constructing truth tables. I don't know.
Oh, I think it was the first one was like if you get Q and not Q implies P, something like that.
Not for 3.2. So 3.2 was direct truth table construction. So for example, 3.2 2a asked you to construct the truth table for the negation of P and Q. So P, Q, same exercise as in engineering 250. List all the possible combinations and then fill in the truth table. Do it in steps, right? So put a column for P and Q because that's just the conjunction and we know that truth table or we can look it up. And then do another operation on that. And now all we have to do is negate this new column that we just wrote. So that's a single operation to keep track of. So that would be the answer for that. And that's just the truth table of an AND. Right, so we're sort of familiar with that. All right, so 3.3, question 2, we were doing truth tables. Oh yeah, so 3.2, we kept getting questions on that one. So question 2, we were given this proposition X, which was equal to P and not Q, or R and P. So the first part was to give a proposition other than X that's logically equivalent to X. And we talked about this yesterday. There's a few ways you could do this. You could distribute this across this. You could use De Morgan's theorem. There's a variety of things you could do. If you do distribution, we can take this and distribute it across this conjunction. So we could get P and R and P. Org with, might be doing this backwards. Nope.
You could do distribution of P in the end.
Yeah. Let's see. Oh, getting my brain tangled up. Let me distribute this across this.
Wouldn't P do?
Am I backwards?
I think parentheses.
So A and B or C, how do we distribute the C?
A or C, or B or C.
Right. So if A and B are both true, then this will be true, this will be true, the AND will be true. If C is true, this will be true, this will be true, the AND will be true. So it's our first term or the second one ANDed with this, so this would be equivalent. And we can distribute again and clean up some of these terms. Right, so you're just trying to come up with a different proposition that's going to be equivalent. So part B was the semi-mysterious, give an example of a proposition other than X, sorry, A was the truth table, B was this. So part C, give an example of a proposition other than X that implies X. So we want something that if it's true, X is also true. So what was a good answer for that? Yeah, P by itself doesn't tell us that X is true. But if we do R and P, right, then we know that this is true, and so the disjunction is true, so the whole X is true. So R and P would be an example of a proposition that implies X. We could always do this, right? If X is true, then X is true, but they said other than X itself. So that's just to eliminate that case. And then for D, we want a proposition implied by X. So if X is true, there we could say P. Because if X is true, we know, well, no, we don't know that P is, yes. We know that either this is true, and if R and P is true, P is true, or this is true, and if P and not Q is true, P is true. So P is a very simple proposition implied by X. Yeah, yeah. So, but there's other ones as well.
On C, could you say not X?
That's logically equivalent to X, so it's kind of a cheat. Yeah, because if P is equivalent to X, then certainly P implies X and X is implied by P. Alright, question 4. Suppose X is a proposition generated by P, Q, and R that's equivalent to P or not Q. Write out a truth table for X. That's potentially interesting. So X is equal to P or not Q. And we're told it's generated by P, Q, and R. So it's some combination of P, Q, and R, but this is also equivalent to it. So if we write the truth table, so anytime P is true, X is going to be true. So it's certainly true in these cases. And anytime that Q is false, not Q will be true. So if Q is false, this is also true. And in any other cases, it's going to be false. So it's equivalent to something that does not depend on R. And you can see that if we group this by pairs, in each case, whether R is true or false, the value of X doesn't change. So that's what you would hope for. Number 6 we talked about yesterday. So find a proposition equivalent to P or Q that uses only negation and conjunction, so throw De Morgan's theorem at it. Right, so not P or Q is equal to not P and not Q, and P or Q is equivalent to the negation of not P or Q, which is thus the negation of this. So there's an answer. Alright, 3.4, number 2, show that common fallacy is not a law of logic. We did an example of that yesterday, right, with it being Friday and having class today. 3.5 was the one that we worked around some examples of. So any particular exercises from 3.5 that you want to see worked out? This was showing direct and indirect proofs of different statements.
Direct for C,
Which number?
for
354C. Alright, so what are we told here? We're told A or B. And we're told C and D. And A implies not C. And from all of that, we claim we can conclude B. We might have done this one. We did. So the basic idea was A tells us C is false. Since C and D is true, C has got to be true. And since A tells us that C is false, A has got to be false. Right? That's indirect reasoning. If A is false, but A or B is true, then B's got to be true, because one of them has to be true. And that got us to B. Yeah?
When you're doing an indirect proof, you can contradict any of the premises, right?
Not really. So if you contradict this, and you get to a contradiction, are you assuming B is true though?
No, like, if you assume B is not true, then can you contradict A, if A, then not C, or C?
You mean to get to your contradiction where you say, okay, therefore B must have been true?
Yeah.
Yeah, any contradiction will work. All you're trying to come up with is basically false equals true.
So when you're doing indirect proof, you assume that B is not true in this case, right?
Right?
So if you prove like A or B to be false somehow, then would that automatically mean that the conclusion had to be B?
Well, let's see an indirect proof. So we'll start off with not B. That's our assumption. And so if B is false, but we also know A or B is true, that's a premise. Since A or B is true and B is not true, that must tell us that A is true. Right, and the reason for that is some kind of simplification. That's disjunctive simplification. And if A is true, and we know A implies not C, that's a premise, then we have not C, that's direct reasoning. But we also know C and D, that's a premise. And if C and D is true, then we also know that C is true. That's something I can never remember the name of. That's conjunctive simplification. And now we have a contradiction, because we have not C and C, and that's false. So we've proven that false equals true. So there must be an error, our assumption must have been wrong.
You just have to get a result that is not B. So
Yeah.
that not B for your indirect proof, and you're assuming it's not B, would that prove that it should have been not B then?
So what we've done is we've said not B implies false, right? And if not B implies false, then this can never be true. Otherwise we would have something true imply something false. So if not B implies false, then not B must be true. All right, the other way to look at this is if we have P implies Q, that's logically equivalent to not P or Q. So if we have not B implies F, this is logically equivalent to not B or false, which is the same as B, or false, which is the same as B. So this proves B. That's the basic idea of an indirect proof. You got homework? Oh, you already? Yeah. So sometimes, and I think I put a note in this on the homework itself. I've seen people try to do an indirect proof by taking all of these things, assuming not B, doing a direct proof on all of this that shows B, and then saying B contradicts not B, right? So there's our contradiction. But that's really just a direct proof kind of bundled inside a much broader indirect proof, right? The goal is really to start off with negating the conclusion and then trying to find some contradiction. And technically, if you find B, right, you've got a contradiction. But you're doing a direct proof and then putting it in the language of an indirect proof. So you usually want to try to do something different that actually works from these and not B and gets to some contradiction. All right, so let's look at 3.8. So questions on quantifiers. So question 2. So M of X says X is a mammal, which I think has 2M. A of X says X is an animal, and W of X says X is warm-blooded. So these are each propositions with a propositional variable X. When you pick an X, you've got a different proposition. If X is a cat, then M of X says a cat is a mammal. Okay, each of those is a proposition. So part A says to write an expression for every mammal is warm-blooded. So what could that look like? Every mammal is warm-blooded.
M of X and W of X.
Close. So this literally says for every X, X is a mammal and X is warm-blooded. So what if X is my goldfish, right? Then this statement isn't true. But you're within one symbol. Yeah. If M of X, then W of X. If X is a mammal, then X is warm-blooded. That's another way of saying every mammal is warm-blooded. All right, and then part B is giving us something in propositional language. So it says this. So what does this funny statement say?
There exists an animal that is an animal and not a mammal.
Correct. There exists an X. Did they say what the universe was? So the universe of creatures or something, right? There exists a creature which is an animal and is not warm-blooded. All right, what about the mother-grandmother one? We talked a little around this the other day. But let's do the whole thing. So m of xy says x is the mother of y. So which of the following are true and translate into English? So let's just translate into English. There exists an x, and they're putting a u in here after the exists to clarify what the universe is. I don't usually bother with that. If we know what the universe is, we can just assume that's the universe. So there exists an x such that for all y, m of x comma y. There exists an x such that for all y, m of x comma y. So what does that say in English? So this says x is the mother of y. What does this statement say for all y, m of x comma y?
It says,
All y x is the mother of y.
Say again?
For all y, for all y x is the mother of y.
Mm-hmm.
Isn't infinity as mother?
So for all y,
But there is no
x is the mother of y. We're not changing x in this statement, right? X is, you know, something. We're saying for all y, x is the mother of y. In other words, x is the mother of, what's the exact universe? All people. Right? Pick a y, x is the mother. Pick a different y, x is their mother. Pick another y, x is their mother. So x is the mother of every y in the universe, all people. So if we throw this existential quantifier in front, what is this saying now?
there exists an x. X is the mother of all.
Yeah, there exists an x such that this is true. In other words, there is a person who is the mother of all people. Is that a true statement or not? It's not. Even if you said that there was a person who's a, whatever the opposite of a descendant is, a prescendant?
Answer.
An ancestor of all people, would that be true or not? Maybe, except you're not an ancestor of yourself. So that would be your case where it's not true. But barring that case, it could be that there was one person who was the ancestor of everybody. All right, so question 2. For all y, there exists an x such that m of x comma y. For all y, there exists an x such that x is the mother of y. So again, we can break this into cases. X is the mother of y. There exists an x such that x is the mother of y. This says any person has a mother. And then if we add the universal quantifier, this actually says any person y has a mother. And then if you add the universal quantifier, it says for all y, that person has a mother. So it's saying everybody has a mother. Which we generally consider to be true. And then the last part, we're asked to write an expression for everybody has a grandmother. So who can do that? We saw everybody has a mother. Yeah.
So I said something like, I said something like everybody has a mother, and that mother has a mother. So it was, see, for any x, no, yeah, for all x, there exists a y such that n x y. I think that's what it is.
XY or YX?
Oh, the yx, I guess.
Yeah. Okay, so
And
this
then
says everybody has a mother.
And then I made a new symbol, z. I think that would be for every y there exists a z such that m z y.
Okay. This says every y has a mother z. But let's not say for all y, because up here we're talking about a particular y. So maybe we want to say y is the mother of x, and there exists a z such that z is the mother of y. Like that.
Is there a way to do that without assigning z to grandmother? I wasn't sure. It didn't say to do that, so I assumed it was.
Well, let's see. For all x, there exists a z such that we kind of need a middle variable in there somehow.
Yeah, I was just.
The proposition is simple enough, so we need to know that z is the mother of y and y is the mother of x. And we got to know what y is. So exists z comma y such that, which is basically the same thing we had up front. All right, what about 3.8? This is going to tie into set theory in a few days. Use quantifiers to state that for every positive integer, there is a larger positive integer. So how do we do that? For every positive integer, there's a larger positive integer.
For every x such that this is above 0, there exists a y such that y is greater than 0 and x.
So for all x bigger than 0, there exists a y such that y is bigger than 0 and y is bigger than x. Perfect. Is that a true proposition?
Yeah.
For any positive integer, there's always a bigger positive integer. This is one of the cool things about integers. Is infinity an integer? No. Is it a number at all? It's a concept. It's a notion of something compared to which there is nothing bigger, which makes it different from any integer, because every integer has something bigger. Every real number has something bigger than it. Infinity is this idea of something for which there's nothing bigger than it, but it's not actually a number. We're going to play around with infinity a lot next week. We're going to have a lot of fun with it. All right, so any other homework questions? That was pretty much all of them.
There wasn't a question that was like, Q and not Q proves P, something like that. I might
I
have
think
had
I
a
know what
question
you're
once
talking
with
about, I
that.
think I said that too. I thought I saw that.
Trying to prove that this is true?
Yes, with the truth table, I think it was.
Okay, first of all, is this true?
P could be anything.
P could be anything. P could be I can fly around the parking lot by flapping my arms. But since this is false, right, false always implies true. So yeah, let's look at the truth table for this. So here's Q, it's either true or false. Here's not Q, it's either false or true. Sorry, let's do Q and P. So false, 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 true, true, false, true, true. So not Q is true, true, false, false. Q and not Q is always going to be false. And so Q and not Q implies P. Well, remember our implication table. So when is if A then B true? It's true in all cases except where the hypothesis is true and the conclusion is false. So this column is always false. Whether P is false or true, false, false, and false, true, the implication is always true. So since in all possible values of P and Q, this statement always has the value true, we can say this proposition is always true. The problem with truth tables, the upside of truth tables is they're very sort of mechanical in how we go about using them. The downside is they usually leave us feeling kind of empty, right? They don't really leave you with this like, oh, it makes perfect sense now, right? We've just got a bunch of T's and F's and we see T's and it's like, okay, I guess it's true. But there's no real sort of necessarily insight coming from that. All right, so back to sets, which we're going to spend some time on. So we were talking about different ways to define sets. We had set builder notation, the set of all x such that x squared equals y squared or something like that. Another easy way to define sets is interval notation. And so we can say something like bracket A comma B. And this means the set of all x such that x is bigger than or equal to A and x is less than or equal to B. So it's everything from A to B. And if we use parentheses, it's a set of all x which is strictly greater than A and strictly less than B. So not including the endpoints. And we can do combinations like this. So this combination would include A but not include B. This would exclude A but include B. So square brackets include the endpoint, round parentheses don't include the endpoint. And this is mostly interesting when we're working over the real numbers. Integers, it's not so interesting, because if you include the endpoint, you get one extra number. If you exclude it, you just start from the next integer. But with reals, this is pretty interesting. So consider the interval 2, 3. And in this case, x is coming from the reals. So this is one of these rare occasions where we'll talk about reals instead of integers. So first of all, how many numbers are in this set? This is a set, it's a collection of x's. How many numbers are in this set? That's infinite, right? There's no number we can answer. We can't say there's a billion elements in this set because there is at least 1,000,000,001, right? So the size of this set in some way is infinite. What's the smallest number in this set? 2. All right, here's a different interval where we're excluding those endpoints. Still has an infinite number of elements, agreed. What's the smallest number in this set?
2 plus an infinitesimal.
Yeah, I mean, it's not 2 because 2 is excluded because we got a curl parenthesis there. But there is no smallest number. It's not 2.1 because we can take 2.05 and that's even smaller and it still belongs to this set. And any number that you claim is the smallest number in this set, there's something between that number and 2. In fact, there's an infinite number of things between that number and 2 that are all going to be in this set and be smaller than the number you picked. So that's a quirky thing about open intervals like this. So this is called an open interval. This is a closed interval. And they're almost exactly the same. The only difference from here to here is we toss in a 2 and we toss in a 3. But they feel fundamentally different because of this fact that this set has no smallest number, it has no largest number. Whereas this closed interval does have a smallest and a largest, 2 and 3. So they behave fundamentally differently, and in fact, there's a whole branch of mathematics called topology that's built around this idea of open versus closed intervals. And starting with this idea of open and closed intervals, you can develop calculus. But you don't have to just talk about sets of real numbers. You can talk about sets of shapes, sets of, I don't know, farm animals, markers, and you can develop a calculus basically for any of these sets using this idea of open and closed intervals, as long as these intervals obey a few simple properties. Like when you combine 2 open intervals, you get another open interval. So this is a concept that we learn early in school, and it seems pretty straightforward, but it's another one of these springboards into a whole branch of mathematics that's totally beautiful on its own and leads to all kinds of wonderful areas of exploration. One of the best being when the things in your universe, instead of being real numbers, are actually functions. And you can define a whole calculus of functions, and it's called functional analysis. And you can look at sequences of functions and limit points of sequences of functions and all kinds of crazy things. None of which we have to worry about, though, because this is discrete structures. So we'll mostly stick with integers, but I wanted to mention that on intervals. All right, I have 35 seconds. Can I do anything useful in that? Yes, I can talk about equality of sets. So if we say A equals B, where A and B are sets, this means for all x in our universe, x is contained in A if and only if x is also contained in B. We know what equality means intuitively. Same stuff over here as here, but this makes it more rigorous. For any x in our universe, x is a member of A precisely when it's a member of B. Right? And it's a member of B precisely when it's a member of A. So this equality of membership gives us equality of sets. And this is why these two sets are the same. Right, so the order doesn't matter. It's just the membership or not membership that matters. All right, so Venn diagrams tomorrow. We'll move on to set operations. We'll move into subsets, and then we'll talk about a cool little paradox that comes out of set theory, and that'll be our Friday entertainment.